In this video, I will cover a 2D high-speed core mill toolpath. A 2D high-speed core mill generates the free-flowing motion needed to machine features, such as standing bosses and cores in a single operation. Core mill requires two chains, an outside chain defining the stock boundary, allowing the toolpath to move freely outside of this area. As well, an inner chain defines the limit of the toolpath. Select Toolpaths, 2D High Speed, Core. If a prompt appears, enter new NC name, select the OK button to accept this default. Leave the default settings in the chaining dialog box. Select the first chain as shown. Now select the second chain. Once the chains have been selected, choose the OK button to continue. The Chain Options dialog box will appear. Select the OK button to exit the Chain Options dialog box. In the Toolpath Type page, select the Toolpath Core Mill. We will now select a 3/4 inch flat end mill from the tool library and set the tool parameters. From the Tree View list, choose Tool. From here, click on the Select Library Tool button and then the Filter button. Select the None button and then under Tool Types, choose the flat end mill icon. Next, under Tool Diameter, pick Equal and input a value of 0.75 as shown. Once complete, select the OK button to exit the Tool List filter. In the Tool Selection dialog box, you should now only see a 3/4 inch flat end mill. Select the 3/4 inch flat end mill and then choose the OK button. Your tool will appear as shown. Input the following comment: machine the elliptical shape boss. Once you have entered the comment, select the cut parameters. Enable corner rounding. As well, ensure that the amount to leave on both the stock and walls is set to 0. And finally, make sure that the percentage of tool diameter is a value of 500. I will now take a brief moment to explain a few of these parameters. Corner rounding replaces sharp corners with arcs for faster and smoother transition in tool direction. Max radius is the largest arc that you will allow Mastercam to insert to replace a corner. Larger arcs will create a smoother toolpath but with greater deviation from the originally programmed toolpath. Profile tolerance represents the maximum distance that the outermost profile of a toolpath with a corner rounding can deviate from the original toolpath. Offset tolerance represents the maximum distance that a profile of a toolpath created with a corner rounding can deviate from the original toolpath. This is the same measurement as the profile tolerance but is applied to all the profiles except the outermost one. XY stepover expresses the maximum XY stepover as a percentage of the tool diameter. Mastercam will use the largest value possible that does not leave unwanted upstands of material between the passes. And finally, Keep Tool Down Within keeps the tool down if the distance from the end pass to the start of the next pass is less than the value here. Mastercam will not create a retract move as defined on the linking parameters page. Instead, the tool will stay down and move directly between the passes at the feed rate. Change the max radius to a value of 0.05. And finally, change the profile tolerance to a value of 0.001. Once the parameters have been adjusted, select the depth cuts. Enable this option. Input a max rough step of 0.25. Also, for the number of finish cuts, input a value of 1. Finally, for finish step, input a value of 0.05. Once complete, select Transitions. Choose the entry method Entry Helix and enter a radius value of 0.25. Also, ensure that Output 3D Arc Moves is enabled. And finally, make sure that the value for Skip Pocket Smaller Than is 0.55. I will now explain a few of these parameters. Entry method sets the entry move that the tool makes as it transitions to new Z depths. If you choose to create a helical entry and there is not enough room, Mastercam creates a ramp entry instead. Entry feed rate sets the rate that the tool feeds into the material. Output 3D Arc Moves is an option where Mastercam creates the helix with an arc of G2 or G3 moves. If this option is disabled, the helix will be created with many smaller linear moves. And finally, Z clearance is an extra height used in the ramping motion down from a top profile. It ensures that the tool has fully slowed down from the rapid speeds before touching the material. Select the linking parameters. Make the following changes. Next, select the HST leads. Change the vertical arc entry value to 0.25. HST leads allows you to specify an entry and exit arc radius value for the 2D high-speed toolpaths. The arc is created vertically to lead on and off the material. And finally, select the arc filter tolerance. Enable line arc filtering settings. If a warning appears, select the OK button. Change the following. Your numbers should appear as shown. I will now explain a few of these parameters. Tolerance distribution allows you to dynamically adjust the toolpath's total tolerance. Total tolerance is the sum of the cut tolerance and the line arc and smoothing tolerances. Move the sliders between the cut tolerance, line arc tolerance, and/or smoothing tolerance fields. The ratios update in 5% increments, and the toolpath's total tolerance remains at its current value. Line arc filtering settings allows you to activate line arc filtering for the toolpath and apply the settings you define in this section to the toolpath refinement. Toolpath filtering lets you replace multiple very small linear moves within the filter tolerance with single arc moves to simplify the toolpath. Smoothing distributes a toolpath's node points, avoiding the clustering and grouping of points that can cause marks and other imperfections. And finally, Create Arcs In creates arcs in the selected plane. Your post-processor must be able to handle the arcs and output the code G17, G18, G19 to select this option. Once the parameters have been adjusted and all the changes have been made, select the OK button to generate the toolpath. I will show you how to backplot and verify your part. To backplot the operation we have done so far, select the backplot icon. Backplotting shows the path the tools take to cut the part. This display lets you spot errors in the program before you machine the part. As you backplot toolpaths, Mastercam displays additional information such as the X, Y, and Z coordinates, the path length, the minimum and maximum coordinates, and the cycle time. It also shows any collisions between the workpiece and the tool. From here, select the Backplot tab and enable the following settings: All Operations, Follow, and Leads. You can now select the Home tab. Ensure that Tool and Workpiece are enabled. You can now press the Play Simulation button. To view your part, select the isometric view and Fit icon. Your toolpath will appear as shown. We will now simulate the toolpath and verify. From the Mastercam Backplot Home, select the Verify button as shown. Verify mode shows the path the tools take to cut the part with material removal. This display lets you spot errors in the program before you machine the part. As you verify tool paths, Mastercam displays additional information such as the X, Y, and Z coordinates, the path length, the minimum and maximum coordinates, and the cycle time. It also shows any collisions between the workpiece and the tool. Ensure that the following settings are enabled: Tool, Stock, and Workpiece. You can now press the Play Simulation button. Your part will appear as shown. You can now exit Verify.